Greetings, stargazers, and welcome to our next lecture in astronomy. This one's going to be discussing the life of the low-mass stars. And we look at the excellent examples of like the end of a star's life, these different types of nebulas that can come off of them. So let's go ahead and dive right in. Give yourselves a little bit of an outline. So first thing we're going to discuss is just how much mass matters in the life of a star. How much, knowing how massive it is, and what happens its ultimate fate. From there, we're going to look at the stellar structure as it evolves over time. What happens to our low mass stars? We're going to stick just there for now. And eventually talk about their ultimate fates. What happens when they've run out of fusible material? And at the very end, we'll talk about a few types of novas. Maybe some supernovas, but not the biggest ones yet. That'll be for a future video. So as usual, let's just test that everyone's paying attention, kind of in the right mindset, and give ourselves just a quick reading quiz. We're going to say the blink of a main sequence star the blink a main sequence star is, the more hydrogen it has to burn, and therefore the blink its lifespan. All right. So pause yourself, give yourself a second to think about this, look at the different permutations, and start piecing together. And I'll hold for a moment. All right, come on back. What you're going to know is that, well, it's going to matter a lot about the more massive. We can throw out things like larger. We're going to say the more massive an object is, the star is, the more hydrogen it has to burn. So it has to be either A or B. And here's the catch. The more massive it is, the shorter its lifespan. Yes, it has more fuel to burn, but it burns through it a lot quicker. So low mass stars are going to be the longer living stars. So we're going to see simulations like this. We'll start with a star forming from the nebulous and growing in size once it leaves the main sequence, turning into these red giants. And at the end of their lives, we're going to see lots of these nebulas. And we'll do things like sketching these lives throughout the HR diagrams. That's going to be a big component of these lecture series of videos. So let's go ahead and finish our first part, the mass matters. And just remind ourselves that, yes, nebulas here, these are the ultimate fate of a star, like our sun. Our sun will eventually turn into a big nebula like this. Now, the core of the star, the core will be hidden in the middle of this, and it'll just be a shell of what remains, a hot shell. So remember, the most important fact of this entire lecture, if there's one thing you need to walk away from this, is that the initial mass, the mass of the star when it forms from protostar to star, that is the crucial factor in that star's life. We're talking about how long the star is going to live. The temperature and the pressure in the core, these things are directly determined by how much mass is there. Temperature and pressure, well, that determines the rate of fusion. Right? If you know how quickly you're consuming something, you know how long you're going to live. And another one, what possible fusion reaction chains? When we talked about the sun, we discussed how we go from 4 protons to eventually 1 helium. We'll discuss one other fusion change in this lecture, and I'll just let everyone know that there are hundreds of different fusion reaction chains. We're only talking about the main ones, but emphasis that I want to make here is that the mass of a star tells you what possible fusion reaction chains exist, what type of matter that star will make. So wrap this all up. Remember that the lifetime of a star is determined by the mass, how massive it is, and its mass ultimately determines the rate of fusion, how quickly you guzzle up your fuel. And another way to say this is just the mass per luminosity. How quickly does that star radiate its energy away? So in terms of lifespans, right? If you have a low mass star, we're talking about stars that are anywhere between about 3 times the solar mass. Remember, circle dot is mass of the sun. So we're talking about stars that are up to 3 times our sun to less than that. And that'll be our low mass stars. And we're looking at a plot of their mass and luminosity and then lifespan. All right. Continuing on with our sequence of the mass of stars. Low masses are less than 3 sols. We can define intermediate mass stars, and they'll be between 3 and 8 solar masses. Anything greater than 8 solar masses, that's what we're going to call our high mass stars. So our high mass stars discussions, that's going to be for the next section, section 17. But let's focus on the low mass stars, right? There's a lot in this plot, so let's go through this. The x-axis is going to be the mass of the star in terms of solar masses. So 10 solar, 20, 50, 60, all the way up to 60 solar masses. In the blue line, we're looking at how luminous the star is, the rate at which it's giving off energy. And the stars that are 60 times the solar mass, they're going to be radiating energy almost 500,000 times greater than the sun. That's how quickly they're producing and releasing energy. But looking at the orange plot, we're going to focus on the lifespan now. Specifically, we're looking at the log of lifespan, and we'll have more to discuss on the log lifespan. But all we're doing is basically rescaling this. And notice, as the mass goes up, the more massive stars have a much shorter lifespan. Go down to lower and lower mass, and the lifespan increases. The less massive a star is, the longer it lasts. That's the crucial factor here. The more massive it is, increase the mass, decrease the lifespan. It guzzles up all of its fuel too quickly. So now I'll start talking about this log stuff. What the heck's happening there? Why are we looking at a log of time of life? So we can look at a plot. Here is the mass and luminosity again, and here it is just exponentially growing. It just keeps growing and growing and growing. And so we can say, well, there's this relationship. We know that the luminosity of a star has to be proportional to its mass to some factor k. Luminosity is mass raised to a power. Well, how do we figure out that power? Well, we could say, look at the mass luminosity and straighten out the curve. Take the logarithm. Take the log luminosity and the log of mass raised to some kth power. Right? If you remember your logarithm rules, a log of something raised to a power, you can pull the power out. Remember, logarithms is the inverse of exponentiation. And so by doing that, we've written the log of luminosity as this k. Remember, k is what factor n's growing by. K times the log of mass. And so by doing that, we've converted this growing exponential curve into this nice, straight, linear line. It's just a linear line. And we know how to deal with linear lines. We could talk about what's the slope of this curve, the rise, right? The rise over the run. And you get the slope. And hey, this k value, it's the slope of this log plots. And that's one of the many advantageous uses of logarithms. They allow us to take curves that are very difficult to trace through, and instead just draw a nice straight line through the data and pull out information we want. So from information like this, we've been able to learn that the luminosity of a star and its mass, they're related by about this mass to the 3.5 power. So to wrap this part up, we can say is that, hey, if we know the spectral type of a main sequence star, we know its luminosity. Calculate its luminosity, that's one way to get its mass. Once we know its mass, we know how long it's going to live. And furthermore, you can actually calculate things like what its brightness is and how far away it is. So these are all different permutations of calculating mass and pulling out other useful information from that star.